All right, the first thing is a reminder that your unit exam is tomorrow. Okay, so period 2, you guys can write into scheduled help if you want a little bit of extra time. Okay, and obviously period 4, that they can write after school for a little bit of time as well. Okay, so make sure that you are ready for that. If you normally write in learning support because you have accommodations, go there. I delivered your exams this morning. Okay, so they are already there and waiting for you in learning support, so go straight there. Okay. Final exam schedule came out. Okay, I don't know if you guys saw that in the announcements, okay, but it is now out, and your final exam is June the 24th at 9 a.m. Okay, so make sure that you have planned around that. Okay, your vacation starts after your exam, not before. Okay, so make sure that you are available that day. I don't know the location yet, but I suspect it will probably be the gym. Okay. In terms of your mock final, okay, what I'm probably going to do once the supervision schedule comes out is I will make a Google form that you put it on Google Classroom, and you guys can fill in when you want to come in and write your mock final. That way it's not like you have to be here for this time, and if you can't make it there, then you're cooked. Okay. I'll make it so that there are multiple writing times, okay, and you can come in when you don't have a test and you can make it work. All right. Remember, though, that in order to be eligible to write the mock final, you must have no missing assignments. And if you have any missing assignments at the end of the semester, okay, when I say this is the absolute last day you can hand in missing assignments, then you will not be eligible to write the mock final, and will not be sent a link to the Google form where you can fill out when you'd like to write it. Okay, you will be excluded from that. So if you have missing assignments, there's your motivation to get them in. Okay, remember that the mock final is not something that goes into your marks. Okay, there's not like a separate thing there, but if you do well on it, it can replace your lowest exam grade. All right, so if you do better on the mock final than your lowest unit exam, I will replace your lowest unit exam with your mock final grade. So you can't lose by writing it. It's good practice. Okay, the questions on there will be very similar to the questions that will be on your final exam. Do know that the mock final, however, is completely machine scored. Okay, there's multiple choice and there's numerical response, but there's nothing I have to hand mark because I just don't have time for that during finals. Okay, this is strictly a machine graded exam. Okay, your final exam will be just like your unit exams except longer. Okay, it'll have multiple choice, it'll have some numerical response, and it'll have some written response. Okay, problem solving worth like 4 marks, 5 marks, etc. Okay, so it'll be just like that. But the mock final, okay, I've got to be able to turn that one over fast. Okay, all right, so yesterday we talked about simple harmonic motion. We looked at the things that affect the period of a pendulum and the period of a mass on a spring. We did some problem solving to do with that. It's not terribly difficult stuff. Today, we're going to look more at the nature of simple harmonic motion from a forces, work, and energy standpoint. So, a lot of the stuff we talk about today is going to ring a bell for you from Unit 2. Okay, we're going to be talking about restoring force. Okay, we talked about that yesterday. It's the force that tries to bring the oscillator back to equilibrium. All right, we're going to look at what can affect that restoring force, and we're going to look at law of conservation of energy in a simple harmonic oscillator. Okay, we've actually already done that for a pendulum, because a pendulum works just like a roller coaster. You'll have gravitational potential energy, and you'll have kinetic energy, and EI equals EF. The same is true for a mass on a spring, but what changes is a mass on a spring is going to have elastic potential energy as opposed to gravitational potential energy. Right? So it works still the same. It's still EI equals EF, but instead of using M times G times H for your potential energy, you'll be using a different formula that calculates elastic potential. All right, so key points for today. We need to understand the relationship between restoring force, spring constant, and displacement in Hooke's law. Okay, Hooke's law is the thing that we're going to be covering about restoring force. Okay, Hooke, if you remember from Science 10, was the guy who invented the microscope. Okay, so he's actually a physicist. I remember the microscope was just an exercise in building combined lens systems for him. It was strictly a physics exercise. But it's the most important gift biology ever received. You're welcome, sincerely, physics. Okay? So, Hooke actually did a bunch of work with springs and restoring force and oscillators and energy. Okay? So we're going to be looking at Hooke's law. Hooke's law governs restoring force. Okay? We call it F spring or FR for F restoring. Okay? And his law is actually mathematically pretty simple. Hooke's law says that the force that's trying to restore equilibrium is equal to negative K, that's the spring constant, the stiffness of the spring that we learned about yesterday, times the displacement from equilibrium, that's X. I know that's going to seem weird, okay? Up until now, displacement has always been symbolized with the letter D with an arrow over top of it. In simple harmonic motion, we use X because we're talking about displacement from equilibrium position. So it's going to be X there. Okay, you just have to remember that X is displacement for this one. Okay, we have to also understand that energy is conserved in simple harmonic motion, as it is in all things, hence the law of conservation of energy. Okay, so we'll still be looking at that. Okay, and obviously that potential energy for a mass on a spring is going to be elastic potential rather than gravitational potential. Okay, it still works the same way. It's still a form of potential energy. All right, so this is Hooke's law. Okay, Hooke's experiment worked like this. It was a very simple experiment, but it was very important as well. He took a bunch of springs and he hung them from the ceiling. Okay, and what he did is he recorded how long the springs were with various amounts of mass on the end of them. All right, what would be pulling on the mass? Gravity. What else is pulling on the mass? If I hang a mass on a spring, it falls, it only comes down a certain way and then it stops. Okay, gravity's pulling it down, what's pulling it up? The spring. Okay, so in a Hooke's law question, okay, you're going to have forces that are acting against each other. Often, when it's specifically Hooke's law, we're talking gravity is opposing the restoring force in the spring. Okay? This is how a scale at the supermarket works. Right? So if you've ever gone to the produce section, okay, like Safeway or Sobeys or No Frills or wherever, okay, you go in there and you put the fruit on the scale. Okay? The scale uses a spring, right? And it pulls the weight of whatever you put in there, pulls the dish down, stretches the spring, and then tells you what the mass of whatever you've put in there is. Okay? All scales work that way. All right, so if if you're using your bathroom scale, rather than hanging, it's got a spring that points upwards. Okay, now I don't know what your scale says when you stand on it. Okay, and that's none of my business, but I know what mine says when I stand on it. I stand on it and it goes, "Get off! Get off!" Does yours not say that? Must just be mine then. Okay, so when I stand on it, what I do is I compress that spring in the same way that the one in the supermarket works, except I'm compressing it and the supermarket is being stretched. Springs work equally both ways. Okay? All right. So what we've got here for Hooke is his experiment was that he found there's a linear relationship between the displacement a spring experiences, that is how much it's stretched or compressed, and the weight that was placed on it. Okay, that's where he got this formula from. What do you suppose the negatives for? Because his formula is negative K times X equals the restoring force. Is force a vector quantity? Okay, so when I hang masses from the spring, gravity pulls the spring down. Which way does the spring pull? Up. Restoring force is always opposite the displacement the spring experiences. Okay? If I have a spring sitting on a table and gravity is not a factor, and I pull it to the left, the spring pulls to the right. It opposes me. Okay? If I try and compress the spring by pushing it to the right, okay, the spring pushes to the left. It always pushes against me. Whichever way I stretch or compress the spring pushes the other way. So the negative always ensures that the vector of the displacement and the vector of the spring are opposite. Okay, because they have to be. Okay? The nature of elasticity is that it always pulls opposite the direction it's being pulled. And it's always going to oppose that displacement. That's how it restores equilibrium. Okay? If I move a mass on a spring right of equilibrium, the spring has to try and pull it back to equilibrium. That's left. It's always going to act opposite the direction the mass is from equilibrium. Okay? So, pretty simple formula, pretty easy to use. Okay? Hooke's law is always going to involve some force, okay, that is pulling on a spring. Now, if I've got the situation in the supermarket, so I have a vertical spring, okay? Let's say that that's the equilibrium position of the spring. No mass in the dish, okay? Then I throw a watermelon in there, okay? And the spring stretches out. So now the spring looks like that, okay? And there's a mass hanging on the bottom of it, okay? What's the net force in that situation? It's just hanging there. Zero. It's just hanging there, right? If it's not accelerating, there's no net force. Okay? So if it's just hanging there, then the force in the spring is equal to, but opposite in direction to, what's pulling on the spring? Gravity. Okay? So you'll often see Hooke's law set equal to another force. Okay? Whatever force it's opposing. Okay, so in a vertical spring, that's usually gravity, right? So in a situation like this, they might say the spring constant is, let's say, 20 newtons per meter. So they'll tell you what K is. And they'll tell you that the spring was displaced, I don't know, 0.08 meters. So it's stretched at 8 centimeters, all right? What's the mass on the spring? Could I calculate that now? Right? I know what K is. I know how far the spring was stretched, so I know both K and I know X. And I always know what G is, because I'm assuming this produce section is located on Earth. Okay? So all I have to do is bring G over here, and I'm solving for the mass of the fruit or whatever it is I put in there. I just picked those numbers randomly out of my head, so for all I know, I could have put a car in that thing. I don't know what the mass would come out to. Okay? Everybody all right with that idea? Okay, what if I have a horizontal spring? Okay, so I've got the mass on the spring, and it's oscillating back and forth on a frictionless table. Are there any forces in that situation other than the spring? Okay, so is the force in the spring then the net force? Okay, so in that situation, I could say that negative K times X equals M times A. Did I just do a Newton's second law question there? Right? K times X, that's the sum of all forces. There was only one force acting. That equals the net force. Could I calculate the acceleration of that mass basically anywhere? As long as I knew where it was talking about? Here's a question for you. Here's the equilibrium position. Here's maximum compression. Here's maximum stretch. So the two amplitudes. What will the acceleration of the object be at equilibrium? Oh, I thought I heard somebody whisper. What is X at equilibrium? 0. What's the acceleration at equilibrium? 0. Why? Actually, it stops for a second here and here. You're right, it does stop during the oscillation. The stopping happens at the two amplitudes, okay? But at equilibrium, is the spring stretched or compressed at that point? If the spring's not stretched or compressed, is the spring pushing or pulling? So there's no net force, so there's no acceleration. These are the kind of things that could end up in a multiple choice question, okay? Checking your understanding of the forces involved in something oscillating back and forth. And they go back to Unit 2. They go back to Newton's second law. Okay? This is a force. It's the restoring force. Okay? You have to see, is it the net force or is it equal to another force? Because the net force is 0. What's going on there? Okay? That's kind of the trick. But you're good at that because you've already been doing it since Unit 2. Okay? All right. All right, so mathematically, Hooke's law, negative k times x, and as we just said a minute ago, the negative is there to ensure that the force always acts in the opposite direction from the displacement. Okay, so on a horizontal spring, that looks like this. Okay, if I push the spring in, like I am here in C, if I push that spring in, then the spring has to push the other way. If I pull the spring, like in B, then the spring has to pull back to equilibrium. It's always going to go against what the object is doing because it's trying to bring it back to equilibrium. It's trying to restore equilibrium. That's why we call it the restoring force. Okay, everybody all right with that idea? Okay, mathematically, Hooke's law is very easy. Okay, all you'll ever do with Hooke's law is make it the net force or set it against gravity. Like basically, that's the only two situations it's going to be involved in. Right? What becomes more important is the understanding of what happens to the value of that restoring force as the object oscillates through its path. Okay? That force goes up and down as that object oscillates back and forth. Okay. All right, any questions on that part? Come on. All right, so elastic potential energy is related to Hooke's law. All right, now if you were in my Science 10 class last year, okay, we did a lab where we stretched an elastic band. We put it between the legs of two desks and we put a spring scale on it and we pulled it. It was like the most boring lab ever. Okay? And we just measured how far we had pulled it and how much force was in the spring. And we made this graph. The lab was actually about work. Okay? And what we did is we built a graph of distance and force. And we found that the further we pulled it would require linearly more force to do so. Was this exactly Hooke's law? Right? Hooke's law says that the force required is negative k times x. The bigger x gets, the bigger F gets. Okay, so we actually used Hooke's law in that lab. We didn't know it, of course, at the time, but that's what we were doing. Now, in that lab, what we did is we wanted to calculate the work done to pull on the rubber band. Okay? We did work in stretching the rubber band because when we stretched the rubber band, what do we put in it? If I'm doing work, work is a transfer of energy. So when I stretch the rubber band, do I give the rubber band elastic potential energy? Okay, and we calculated the work that we did by going average force times distance. Okay, that formula should look familiar because we've used it in this course as well. Right. When we calculated the work, we did it by calculating this area here. Okay, now, how do I calculate the area of a triangle? Well, I think somebody knows. Sophia, how do I calculate the area? Base times height divided by 2. Okay, the base is distance, all right? And the height is force. And I'm dividing that force by 2 because the whole experiment I wasn't using this much force up here, okay? Nor was I using this little force down here. The average force I used was halfway in between them. Okay? So, if I do that calculation, I'm basically taking half the force, half the maximum force, and multiplying it by distance. Okay, so let's look at that. According to Hooke's law, okay, force is K times X. But I used how much of that when I did this area calculation? I didn't use this full value, I used half of it. Okay, so that's half the force, and I multiplied it by the distance. Well, when we're talking about simple harmonic motion, distance is x. Is this formula right here also this formula? Right? The average force is half of the maximum force, and the restoring force is k times x. So if I go 1/2 k times x, that's the average force. And then I multiply it by how far I stretched it. That's x again. 1/2 kxx is 1/2 kx squared. Okay? That formula calculates the potential energy in any elastic object by taking the force, the average force you used to stretch it, and multiplying it by the distance you stretched it or compressed it. Okay? It's really just the amount of work you did to stretch or compress the elastic object. Okay? When you do work on an elastic object, you give it potential energy. Right? That's what that guy there with the bow is doing. Okay? A bow can launch an arrow because when you pull on the string, you pull the ends of the bow together. You change the shape. Bows are elastic. Okay? You're exerting a force through a distance, changing the shape of the bow, okay? Giving it elastic potential energy. When you release the spring, the bow snaps back to its original shape, propelling the string and the arrow on it forward. Okay? Simple work energy theorem questions that we would have done in Science 10. This is kind of related to that. Okay? Everybody all right with how elastic potential energy works? We treat it exactly the same as gravitational potential energy. It's there, but it's not doing anything. Okay? But it can. It can do work, and it can turn into, what does potential usually turn into? Kinetic. Yeah. Okay? Bow and arrow, right? If I pull back the bow, it's got all kinds of potential energy because of the work I did. When I let it go, it does work on the arrow, and the arrow will have that amount of kinetic energy. If I did 100 joules of work on the bow, the arrow will have 100 joules of energy when I let it go. Okay? Everybody all right with that? Okay. Now, you're never going to be asked to derive this formula like I just did. Okay? The purpose of this is to show you where it comes from and how Hooke's law, along with work energy theorem, goes together. Okay? That's why we take work energy theorem in Unit 2, okay? So we can apply it to this, and so we know how it works. All right. Law of conservation of energy never changes. Okay? It's a law. You have to obey it. Okay? So, law of conservation of mechanical energy says that your mechanical energy is the sum of your potential energies and your kinetic energy. Okay? Now notice I said potential energies, plural. Is it possible for an object to have more than one kind of potential energy? It absolutely is. Okay? We used to, when we had the IB program here, okay, we used to give the kids a question like this. Okay? And we would have a cart on a hill with a compressed spring. Okay, so we'd say you push the cart into the spring using this much force, you compress the spring this far. Okay, when the cart is over here at this height, okay, there's another spring here, and we would ask you, how far do you compress the second spring? That sounds a lot harder than the question actually is, because it just throws people, because they're just, oh my God, I'm so overwhelmed, and they quit. Okay, but really what we're looking at here is you would have some gravitational potential energy because of your initial height. You would have a lot of potential energy here, okay, from the elastic nature of the spring, okay, and then when you get here, you would have the same amount of energy that you have here. You'd just compress the spring a different amount. Maybe it's a different spring, give you a different spring constant. Okay, but in the end, this is still conservation of energy question. It just never involves any kinetic because it starts out and ends with a compressed spring and a stationary cart. Okay, but it totally throws people. It's like, oh, I have more than one kind of potential energy? Of course you can have more than one kind of potential energy. All right, so the setup is the same as a roller coaster question from Unit 2. All we're doing is substituting 1/2 kx squared in for m times g times h. Okay. Now, when we did the roller coaster questions, did we very often cancel mass because it was in every term? Can we do that now? Mass isn't in every term. Mass doesn't affect your elastic potential energy. Okay? So on this one, I can't cancel mass. It's not in every term. What is in every term? What's every single one of those things multiplied by? 1/2. I could cancel the halves. You can still cancel something, okay? But just not mass this time, right? The manipulations, same as a roller coaster question. You're moving things around. You're going to be asked to solve for a v or an x or maybe mass. Okay, you'd have to maybe do another calculation to get a mass and plug it in there. It's still just a roller coaster question. It's just instead of gravity, you're using elastic instead. Okay. All right, so if we're looking at an oscillating object, like we see in this picture here, all right, at this point here, they're telling us that the speed is 0. And we can see that the spring is stretched, okay? We can also see that the force is pulling the object back to equilibrium, okay? So that would be the object at its maximum. Thinking of a word we learned yesterday, starts with A. Maximum displacement from equilibrium is called the amplitude. Yeah. Okay. So that would be an object at its maximum amplitude. At an object's maximum amplitude, it is stopped because the spring and the restoring force in it have been slowing the object down until it stops for an instant before it turns and goes back to equilibrium. So at this point here, since it has no speed, it has no kinetic energy. What kind of energy does it have? Spring is stretched a lot. What kind of energy does it have there? John, what kind of energy does it have there? Potential. Potential only. Elastic potential energy. Okay, so this is where all of the mechanical energy would be potential. Now, as the object moves back towards equilibrium, it picks up speed. But the spring is less stretched, so it has less potential, more kinetic, but does it have the same amount in both places? Same amount of mechanical energy in both places? Absolutely it does. Okay? When I get to equilibrium, so that's right here, it says V max. So now we're moving at our maximum speed. That would mean all of our energy is now kinetic. Okay? How come at that point we have no potential? What's X when you're at equilibrium? 0. Okay? Spring's not stretched, spring's not compressed, it has no energy in it, it can't exert any force, so we're moving at our maximum speed and all of our mechanical energy is kinetic. And then, as we move the other way, we're doing the same thing, except instead of stretching the spring, now we're compressing the spring. Okay? We'll get to our maximum amplitude on this side of equilibrium. Spring will be completely compressed. All of the energy will be potential again. Will be stopped, no kinetic, okay? And it'll just keep oscillating back and forth. It's the nature of these energies that keep a simple harmonic oscillation going. If you had an isolated system and all you did was push that spring in and let it go, it would go forever. Okay? It would never lose any energy in an isolated system, and it would just continually convert the potential energy into the kinetic energy, back and forth, back and forth. Okay? In the same way that if you had a roller coaster and it was an isolated system, if you gave it a little push from the top of the first hill, okay, it would just go continuously and never stop. Okay. All right. So let's look at an example here. Not that one, not that one. Okay, so this is not an energy question, spoiler alert. Okay, write it down and give it a try. Okay, see if you can figure out what you need to do with this one. I'll give you a few minutes and then we'll go through it together. Mr. Deirdre, if you can pause this, give him a couple minutes, please. All right, so this is just a Hooke's law question. Okay, they're telling us that we have this spring. Okay, the spring is normally this long. They don't say how long it is, they just say at equilibrium. Okay, and then they say you pull on it so that it is now 1.5 meters longer. Okay, so it's out here, and then this, it is now displaced 1.5 meters. Okay, and it says it was pulled, so that means it was stretched, not compressed. Okay, so I know what X is, okay, and they tell me K. Okay, newtons per meter, that's a spring constant. All right, so I can calculate the restoring force in that spring by just going negative K times X. Okay, now here's the thing that the diagram is important for. I pulled this spring this way. Okay, so I'm going to say to the right. My restoring force is then going to be to the left. Now, if you just wrote negative, that's fine too, because they didn't give us any actual vectors in the question. All right, so I'm just going to go negative 30 times 1.5, so that's going to give me negative 45 newtons, or 45 newtons to the left. Okay, everybody all right with that one? Okay, Hooke's law is pretty straightforward. Okay, it's either going to be the net force or it's going to be working against gravity. Okay, they're really the only two situations we ever encounter. All right, I would like you guys to try those two questions, okay, based on Hooke's law. Okay, Mr. Deirdre, if you can pause it here and give them a few minutes to try those, please. Okay, so there is a trick in the first one. They give you X in centimeters. Since spring constant is in newtons per meter, okay, your displacement also needs to be in meters. All right, so sorry, not D. X equals 0.55 meters. Now they do not give a direction on that, so we're just going to work with positive and negative here. Okay, we also know what K is. It's simply 48 newtons per meter. Restoring force is negative K times X, so 48 times 0.55. Okay, and that's going to give us negative 26.4. 26.4. Okay, and that's going to be newtons, okay, because it's force. Right? The newtons per meter and the meters are going to cancel, okay, and we'll be left with newtons. Okay, how are we doing on number 2? Anybody want more time on number 2? Okay, I'll give you one more minute. All right, so a spring requires a force of 100 newtons to compress it. So if I compress it using 100 newtons, how hard is it pushing back? 100 newtons the other way. Yeah, okay, so that's telling me the restoring force, because the restoring force that is applied to me is equal and opposite the force I applied to it. Okay, so that's going to be negative 100 newtons, because it's the 100 newtons they gave me was positive. The restoring force has to be the other way. Okay, and then you're going to compress it for centimeters. All right, so X is going to be 0.04 meters. That's positive. That's the way I pushed it. All right. So now, when I do this calculation where Fs equals negative K times X, if I'm solving for K, I'm going to divide both sides by negative X, so that I'm just solving for K. All right. So negative X. Now I'm solving for K. So negative 100 divided by negative 0.04, okay, is going to give me my 2.5 times 10 to the 3 newtons per meter. If you ever get a negative for K, you simply forgot a negative somewhere along the way. Okay? K is neither positive nor negative. It is a physical property of the elastic object. Okay? It works whether that object is compressed or stretched or bent or whatever. That's just the amount of force per meter you need to do it. All right, so that number can never be positive or negative. It's kind of an absolute value, okay, kind of a deal. All right, everybody all right with how that one worked? Okay, so Hooke's law, okay, pretty straightforward stuff. Okay, here's another Hooke's law question. All right, it's a little different than the last two you did though. Now, this is a true Hooke's law experiment situation. Spring is hanging from the ceiling, right? And mass is being put on it. We are looking for the spring constant of that spring if it stretches it half a meter. All right, I'll give you a couple minutes on that one. Mr. Deirdre, I'll get you to pause it again, please. Look at this one. So the situation, and a lot of the way to solve this question is to understand the context of it. Okay, you have a spring hanging from the ceiling. Then you put a mass on it and you stretch it further. Right, so this would be its equilibrium position, and then this, okay, would be x, and it's half a meter. What's causing this spring to be pulled? Gravity. All right, so that means since it's not oscillating, okay, that there's no net force, and the restoring force in the spring must be equal in magnitude, but opposite in direction, obviously, to the force of gravity. All right, so we want to know the spring constant. All right, fine. So we're going to go negative k times x equals m times g. Since I'm solving for k, which can't be positive or negative, I can make my life a little bit easier and not even worry about this. I already know they're opposite in direction, and I'm solving for k. All right, so I'm simply going to divide both sides by x, and I'm going to be solving for k then. All right, so k will equal, okay, the 510 grams, obviously that needs to be in kilograms, 0.510, okay, times 9.81, if it's Earth, or we assume it is, and divide that by 0.5. Now, I could have also done this and said that this force is negative and this displacement is, I'm bringing the negative over, and that would have been fine as well, okay? But in a situation like this, I'm like, k is going to be positive no matter what, okay? The negative actually doesn't matter in this situation, okay? The negative does matter if you're solving for x, because that would be directional, okay? All right, so when we plug in our numbers here, 0.510 times 9.81, okay, and then divide that by 0.5, so we should get 10. Okay, so K would be 10 newtons per meter. All right, everybody all right with that? So that would be the same as a produce scale at the grocery store. Right? That's how all of those scales work. They're just a hanging spring. All right, want to go over question number 1 here, because this is also a Hooke's law question, but now the object is actually accelerating. Okay, so it's a horizontal frictionless surface. All right, so I'm going to get you to write down question number 1, okay, and you can maybe label this as Hooke's law net force example, so that you can refer back to that later. Okay, so we'll just call that Hooke's law, okay, F net example. Okay, I'll give you a sec here to get that copied down. Okay, so let's have a look at number 1 here. So first off, they tell me it's a horizontal frictionless surface. So horizontal means gravity's not involved. Okay, so I know force of gravity isn't here. And there are basically no forces. This is basically an isolated system. So the only force in that system is, what's the only thing making that mass move? The spring. The restoring force in the spring is the only thing that makes this system go, right? It's horizontal, so no gravity, it's frictionless, there's no drag, okay? It's just going to go forever. So here's what I've got. I know the mass, okay? It's 0.724 kilograms, okay? And it's attached to a spring that has a spring constant of 8.21 newtons per meter, okay? We're looking for the displacement, so x, when the acceleration is 4.11 meters per second squared to the left. Okay, so if it's accelerating to the left, x must have a vector of, the only way a mass is accelerating this way is if it's displaced to the right. The spring's got to be pushing it or pulling it the other way. Okay, x and f are always opposite. Right? If the mass moves out to the left, then the spring is moving it to the right. Okay, so I've got these numbers here. I know that this is that the spring is the only force acting, so that means that the restoring force is the net force. This is a lot like Unit 2. I've got to identify the forces that are involved and figure out their vector sum. That's the only one, so it is the net force. And then I can say negative k times x equals m times a. That's one of the ways to calculate net force. Now, I know the acceleration, I know the mass, I know the spring constant, I'm just looking for x, right? So I'm going to bring negative k over to this side. All right, that should give me x, all right? Now, I've got to be mindful here, this is to the left, okay? So I'm going to make left negative. Right, so I'm just going to do this. Left is negative, right is positive. And then I'm going to plug in my numbers. So x equals, okay, 0.724 kilograms, the mass, times negative 4.11 divided by negative 8.21. Right, because I brought that negative over with k. K in of itself is not negative, but I brought the negative over with it. Right, should I get a positive value now? All right, and that fits then because the force should be going the opposite direction. All right, so 0.724 times negative 4.11 divided by negative 8.21. Oh, what did I do wrong? Oh, I put the minus sign instead of the negative sign. That's what I did. Sorry, guys. Divided by negative. That's better. 8.21. All right, so the displacement would be 0.362, and we have 3 significant digits, meters to the right, because the acceleration was negative and that was left. Okay, everybody all right with that? That's about as tricky as a Hooke's law question gets. All right, I would like you to write down question number 2, and you can put a label on that as conservation of energy example, okay, because it's conservation of energy question. We'll go through that. All right, so let's have a look at how this one would work. Okay, I have a 50-gram mass. Do I want the mass in grams? It's got to be in kilograms. All right, so my mass is actually 0.050 kilograms, okay? And it has a spring constant of 4 newtons per meter. All right, so K is 4.0 newtons per meter, okay? The mass oscillates with an amplitude of 1.12 meters. All right, I'm gonna write A for that, okay? A is the maximum value of X. Okay, X will never be bigger than that number for that particular oscillation. It's the maximum X value, right? And that is 1.12 meters. Now, here's where understanding comes into this question. At the maximum amplitude, how fast is the object moving? Okay, so if this thing's oscillating back and forth, okay, and it's okay to draw this stuff out, guys, okay? This would be the maximum amplitude of compression. Okay, this would be the equilibrium position. Whoa, suddenly that got really big. Okay, this would be the maximum amplitude stretched. So as this thing's oscillating back and forth, when it gets to here and you can't compress the spring anymore, how fast is it going? 0. This is where it stops for an instant before it turns around and goes back to equilibrium. Same is true out here. This is the furthest out it can go because it stops there. Okay, before it turns around and comes back the other way. So I have to remember, if I'm ever given amplitude, this object has no speed and thus no what kind of energy? No kinetic energy. At the maximum amplitude, all the energy the object has is in what form? Potential. Okay, so it only has elastic potential energy at this point, no kinetic. Okay, then it wants to know its maximum speed. Okay, where does maximum speed occur? At equilibrium. Okay, and at equilibrium, x is what? 0. So it has no what energy at equilibrium? No potential. All right, so now if I have that understanding, okay, I can set this up and say the mechanical energy initial equals the mechanical energy final. I can do this just like a roller coaster question, say initial potential plus initial kinetic equals final potential plus final kinetic. Okay, that's all still true. But initially, the object's not moving, so it has no kinetic. And finally, when it's at equilibrium, it has no displacement, so it has no potential energy. Okay? And I'm starting this out pretty easy. The initial potential equals the final kinetic. Okay? Now, what's the formula for kinetic energy? Oh, it's been a long time since we used that one. Okay, 1/2 mv squared. I'm putting an F beside it because in this situation it's the final. All right, initially this thing has only potential energy. Well, that's 1/2 kx squared. All right, and we know in this situation x is the value I put up beside a because we were at the maximum amplitude. All right, so I want to solve for how fast it's going. That's v. Can I cancel the halves? Right, if I do any manipulating, they're going to cancel anyway, right? I'm moving the m over, okay? The halves are going to go away. So now I've got that vf squared is kx squared over m. I just want vf, sorry, so I do what? Square root. Okay, so when I'm solving this at the end, okay, what I've got is vf equals the square root of kx squared over m. Okay, this is just like a roller coaster question where you had no speed at the top of the first hill and you're looking for the maximum speed at the bottom. Okay, so plugging in our numbers here. Okay, k was 4. Okay, so 4 newtons per meter times 1.12 squared divided by 0.050. Okay, what do you suppose the most common mistake is? Not squaring x. Yeah, so common. All right, let's plug in our numbers here. So, square root of 4 times 1.12 squared divided by 0.05. All right, so the maximum speed of that object at equilibrium is 10 meters per second. Okay, does that look a little familiar from Unit 2? Other than we're using elastic potential instead of gravitation. Okay, it's really not a lot different. Okay, we're going to skip. No, we could probably do numbers. Yeah, we'll skip. We'll do a different one. But not. Okay, this is actually, we're going to do this one another day because I actually do really like this question, but it's like 3 parts to it. So we'll actually skip that one for now. Okay, don't like either of those either. No, not those. Where's the one I want? Okay, actually, the handout I gave you, or that you got yesterday, okay, I want you to see the back side has got these questions on it. Some of them are Hooke's law, some of them are energy, okay? And I'm gonna tell you the numbers I want you to work on right now. Okay, so from that worksheet, I want you to do 3, 5, 6, 7, 8, 10, and 16 for now. Okay, we'll probably end up doing the rest of it. Okay, if you get done those ones, you can work on the other questions, but I definitely want us to go through, okay, those 7, okay, together at some point. Probably not today, but those are the ones I want you working on for the remainder of class today.